Locus of a point P whose distance from a fixed point C is called circle. Let's assume that this point C here, this is a constant point, and then there is another point P such that the distance between P and C is equal to, let's say, 10 centimeter. And we call this distance R, but here R means 10 centimeter. Now P can move in such a way that it maintains its distance from the fixed point C 10 centimeter all the time. Then that path on which it can move, keeping its distance from C as 10 centimeter, is called circle of radius 10. Now here Q is a new position of P where P has moved. Then the distance of Q from C must be 10 centimeter again. B is another point such that its distance from C is still 10 centimeter. Then B is also a point of the same circle. And A is another point such that distance of A from C is still 10 centimeter. Then this path on which the point P can move and can occupy new positions but always maintains its distance of 10 centimeter from the fixed point C will be called circle. Now the circle has certain properties, and before we get into the properties of the circle, we should know a few terms about the circle. The fixed point C is called center of the circle, and the fixed distance between PC, which we already have explained, is called radius of the circle. Now if there are 2 points on the circle, just like there are points P and Q, then the line segment joining these 2 points will be called chord of the circle. Now remember this, that the line segment means that it doesn't extend beyond Q on that side and doesn't extend on beyond P on this side. So this is only a portion of the line. That's why it is called line segment. It's contained, and it ends on both sides. Therefore, the line segment PQ, which joins both the points P and Q, where P and Q are points on the circle, is called chord of the circle. And of course there will be infinitely many chords, because there will be points on the circle all over the place, and any line joining them will be called chord. Now here we have 2 points A and B, a line segment, not segment this time, a line passing through those points A and B. It continues to extend on either side. That is the difference between the chord and the secant line. A line passing through any 2 points of the circle is called secant line. And now the last one, a line touching the circle at one point is called tangent line. It's a limited position of the secant line, because if you move B closer to A, then the secant line just gets outer and outer of circle. But we'll discuss these things in detail at some later stage. For now we are concerned with one property of the circle, and that property of the circle states, let's write down the property. It's property of circle. And this first property is that a line of tangency, or a tangent line to the circle, is always perpendicular to the radius of circle at point of tangency. So let's assume we draw another circle here. Let's draw a circle here, and here this is a circle, and then there is a line that is acting as a tangent line. So let's say that this is the line which is tangent. So it should only touch the circle at one point, and here this is the line of tangency, and let's say that this is the center of the circle here, and this is point of contact between circle and the tangent. So let's call this T, and let's call this C. Now the distance CT, as you know already, will be called radius. And if we have 2 points, A here and B is a point here, then the line AB is the tangent line, and CT is the radius of the circle, and T is the point of tangency, like that is the point where the line AB is touching the circle. Then what this property says, a tangent line to the circle is always perpendicular to the radius of the circle at point of tangency. What this property says is that this angle here is 90 degree always, and it is 90 degree on either side. This is 90 degree here, because the angle on one side of line is always 180 degree. Therefore 90 degree would be on this side and 90 degree would be on this side. This is called the first property, the tangent radius property of the circle, and it does have its own implications. Let's solve some of the questions by using these properties. So let's assume that we have a question. Here we got a question here, question number 1, and in this question we do have a circle. Let's draw a circle here, and we have a triangle, and that triangle is such that this is, let's say that this is, here we have this is radius, this would be radius. Let's call this point as A, this point as T, and this point as C. And what will be, according to the property we have just learned, this angle must be 90 degree because AB is a tangent line, and this tangent line is touching the circle at point T, where CT is the radius, and radius CT is always perpendicular or at an angle of 90 degree to the tangent AB. Therefore this angle is 90 degree, no doubt about that. Now if one of the other angle is given, here let's say that this angle is given, this angle is equal to 30 degrees. Then the question is, what is this angle here? Let's call this angle as X. We can answer this question, and we can certainly find what the angle X is by using combination of two things. One, we already know that the angles inside a triangle, any triangle, their sum is always 180 degree. So obviously we know two angles. We know one angle is 30 degree. We know the other angle is 90 degree because of this property. And then the third angle in this triangle is X, and they must be equal to 180 degree. Now X must be equal to what? 180 minus 90 minus 30, or that would be equal to 60 degree. And if you leave that 90 out, because 90 plus 90 would be 180, if the sum of this 30 and X must be 90 in itself, and that's called complementary angles. So if one angle is 30, the other must be 60 degrees so that their sum could be 90 degrees. That's what is called the complementary angles of a triangle. So the x is equal to 60 degree, and you will have many times many questions in whenever the question is asked about the circle, in which that you will be given one angle, and using the tangent radius property you can find the other angle of the triangle. Now let's do another question in which a combination of this, with the help of this property, we can apply Pythagoras theorem, because the Pythagoras theorem only applies to the right angle triangles, I mean the triangles which make 90 degree angle. So let's have another circle here. Let's make this circle here, and in this circle this is the center here, and let's make this as a triangle, and this is a triangle in which this is the point C, this is T, and this is another point P. In this case, the distance between P and T is given, that is given 8. The distance between C and P is given, that is given as 10, but we don't know what the radius is, like what is D, that we don't know. In order to find, if we didn't had this property, we would never know that this angle is 90 degree. And if we couldn't know about this angle, we couldn't apply Pythagoras theorem. But because this property tells us that CT and PT are perpendicular, because PT is tangent and CT is radius, and this property says that tangent is always perpendicular to the radius at point of tangency. Therefore, we know for sure that this angle is 90 degree. And if this angle is 90 degree, then the triangle CPT is a right angle triangle, and we can apply Pythagoras theorem. Therefore, by applying Pythagoras theorem, we have hypotenuse square is equal to base square plus perpendicular square. Remember that the side of the triangle opposite to 90 degree is always the hypotenuse. So this is hypotenuse. Therefore, we can either write it as CP, because name of this side is CP square, is equal to base is CT, and this is square, plus perpendicular, which is PT square. Now this is CP is 10 and its square would be 100, and CT we don't know, but we have D denoting this length, therefore we can say this is D square, plus PT, that is given 8 and its square would be 64. Therefore, now it's simply solving for D square. Therefore, D square would be equal to 100 minus 64. Therefore, D square is equal to 36, and D would be equal to 6. So we can find another angle in a triangle by using tangent radius property, and we can find the missing length of the triangle by using the tangent radius property. And there will be many situations in which we will find multiple other uses of this property, and there are couple of more things to know about this, that if we have a circle, let's draw another circle here. If we have this circle, then let's call this as center C, and let's call this point as P. And this distance CP is obviously called radius of the circle. If we have another point T or A or B, whatever, if distance of that point A, if let's say that this is a point A, the distance of point A, like AC distance, if AC distance is less than PC distance, remember that PC is equal to radius. Now distance of A from C is less than radius, then A is called interior point of circle. If number 2, if AC is same as PC, then as it is clear from the definition, then A is a point on the circle. And there could be only one tangent you can draw from the point A. If point belongs to the circle, if any point is on the circle, then it is enough to say that there is only one tangent. If A is a point on the circle, then we can draw a unique tangent through A. But if A was interior point, there is no tangent. However, there is an interesting situation in the third case. If AC is greater than PC, like PC is the radius, but distance of A from C is greater than the radius, then A is called is a point of exterior. Then A is called a point in the exterior of the circle. And from any point in the exterior of a circle, we can draw two tangents. For example, if we draw another circle here, let's draw his circle here, and let's say that this is a point A which is outside. So here, of course, if this is C and this is P, the PC distance is smaller and A is lot bigger distance. Then in that case, the tangent that we can draw from A is this. And this is not the only tangent where we can draw. In fact, there will be another tangent that we can draw from the same point, and that should meet the circle on this side. Therefore, it is clear that there are possibly two tangents we can draw from a point if the point is in the exterior of the circle. Let's call this point as the point Q. Now here AP is one tangent and AQ is another tangent. Let's consider that this distance of C from Q, this distance is equal to 5. Then obviously the distance from C to this side is 5 as well, because this is the radius. CQ is the radius, this is the radius as well. So what do you think that what should be this angle? We have already established this fact in the property that the tangent AQ and the radius CQ make an angle of 90 degree. The tangent is perpendicular to the radius at the point of tangency. If AQ is the tangent touching the circle at one point, CQ is the radius, then there is an angle of 90 degree. And similarly for this other tangent AP, AP is the tangent and CP is the radius. Therefore, this angle must be 90 degree as well. If that is the case, then line joining directly from C to A, this line. So whatever this angle here is, but we know for sure that CPA and CQA are both right angle triangle because they involve an angle of one angle of 90 degree. If that is the case, let's call this as X and let's call this as Y. Now if we take a look from triangle ACQ, we know that hypotenuse square is equal to base square plus perpendicular square. Therefore, hypotenuse is opposite to 90 degree. Remember that. That is CA. So CA square is equal to CQ square plus AQ square. What is CA? CA is, let's call this CA. We want to, if we have this, let's say 20 centimeter, that's given. The distance between center and the point. So this is, let's say 420 square is equal to CQ, which is 5. So its square will be 25 plus AQ. AQ, let's find out what AQ would be. AQ square would be equal to 400 minus 25. So AQ would be equal to 375 square root. So if you consider from the other triangle, from triangle ACP, if we take a look on this side, the hypotenuse square is equal to base square plus perpendicular square, and this is AC is because here up 90 is here and opposite to 90 is the hypotenuse, that is AC. AC square is equal to PC square plus perpendicular is AP square. This AC is 20 again, so this would be 400 equal to PC is 25 plus AP square, and here AP square is equal to 400 minus 25, and AP is equal to 375 square root. So what do you conclude from 1 and 2? These both AQ was a tangent, AP was a tangent. Don't you think that we have concluded that if a point is in the exterior of the circle, then the two tangents drawn from a point in the exterior of circle are of same length. See you in the next property of the circle.